if we want to prove this rational root theorem that says, for example, the possible rational roots of a polynomial can be factors of the constant divided by factors of the leading coefficient. So let's try and prove it. Prove. Okay. So first of all, let me write here the polynomial function in general form. And the general form is going to be as follows. Plus an minus 1, x n minus 1 plus dot 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 plus a1x plus a0. So this is a polynomial in the general form. And let's assume it has a rational root or 0 that is x is equal to the m divided by n, where m and n are element of the integers and n is different from 0 with this assumption. So now and now let's apply here the remainder theorem. Let's write, for example, p of m divided by n, and let's plug here in this polynomial function in the general form. So we have an m divided by n in exponent n plus an minus 1 m divided by n in exponent n minus 1 plus dot 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 plus a1 m divided by n plus a0. And since x is equal to the m divided by n, so since one solution here is, or m over n is a root of this polynomial function, if we are plugging here in the remainder theorem, this is going to be 0. But since this is going to be 0, so we automatically we can apply the factor theorem that says the factor x minus m divided by n is a factor of the polynomial function p of x. And now, since this is a factor, now if we write it according to the remainder theorem, we already know the polynomial function when, for example, the divisor d of x is equal with x minus m divided by n. This is going to be a factor, and we can write the polynomial function in the form of the factors x minus m divided by n times the quotient of the factor q of x. But this we can adjust a little bit better. So this n I can write here in the front of the x, and this I can write nx minus m times q of x. But now let me write this polynomial function in the form of the factors of a divisor and the quotient of the function. And now p of x is going to be nx minus m times the quotient. We already know when we divided this polynomial by the linear binomial x minus m n, we already know the quotient is going to be 1 degree less. If it's 1 degree less, we have an x n minus 1 plus an minus 1 x n minus 2 plus dot 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 plus a1. And now simply we are going to distribute nx minus m in this equation here, in this expression here. If we are distributing, p of x is going as follows. nx times an xn minus 1 is n times, so let me write better, n times an xn, because x times xn minus 1 is xn, plus n times an minus 1, and this is going to be xn minus 1, plus, let me go a little bit in the last one, this is going to be nx times a1, nx times a1. And now I'm going to multiply by the second term, m times minus m times an x n minus 1. So let me write a bit different color, maybe it looks better. So this is a minus m an x n minus 1. And I'm going in the second one is a minus m times an minus 1 x n minus 2. And then it goes that plus dot 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 plus the last constant m time, in fact is a minus m times a1. And now we are looking here a little bit of what do we have. Now as we see here, n times an, we already see, so n is a factor leading coefficient. So n, I'm sorry, let me write a little bit better this one here because it's not very good. Okay. So maybe I can erase now. Good. So n is a leading coefficient factor. But if we are looking at the last one here, this one m is a factor of the constant. And we already know x was equal to the m divided by n. And this one is a leading coefficient factor. And here is a this is a, so let me erase here. So as we see here in the end, m is a factor, the coefficient factor, the factor coefficient, and this is a leading coefficient factor. And this is just a coefficient factor. And we are proving the rational root theorem that says is a possible solution is the factor of the coefficient divided by the leading coefficient factor.